Okay, so this is just a quick review of calorimetry. All right, so essentially what calorimetry is that it's a method for measuring the change in enthalpy during any process. All right, so the quick diagram of how a calorimeter works is that you've got some insulated vessel. All right, picture a styrofoam being around this, and then you've got a container of water in the middle, and then you've got your reaction or your process occurring right here. All right, so this could either be some hot piece of metal that's giving off heat, or it could be a place where a chemical reaction is occurring, and we're going to any heat that gets generated would get transferred to the water out here, and since it's perfectly insulated here, that would end up resulting in an increase in the water temperature, and that we can then end up using that increase in the water temperature to figure out how much heat was released by whatever our process was right here. So in order to do this, one assumption that we're going to make is that you're going to start with liquid water here, and you're just going to go to liquid water that has a different temperature. All right. And so the amount of heat that you could assume that the water absorbs could be given by the following. All right, so the equation for when things change temperature at a constant state of matter is, you might remember, Q equals mCp delta T. All right, M would be the mass of the water here. All right, that would be a known. Cp is the specific heat of water. That is a value that is known. Also, the specific heat, which is that Cp is also given in your data booklet. This is in table 2. Okay, I wanted to point out also that a lot of the thermochemical equations, like for example the amount of heat that is absorbed or released when things change temperature, you can see in this equation right here. All right, so using that equation right there, if the water, if some process occurs and the water temperature increases, we can figure out the amount of heat absorbed by the water from this equation right here. And since the amount of heat that's gained by the water is equal to the amount of heat lost by the system, or another way that you could say that is the opposite. The amount of heat lost by the water is the amount of heat gained by the system. Either way, this equation right here would tell you how much heat is either lost or gained. Oops, sorry. By the way, that's Beckley right there. So this is this equation right here can be, if we assume that the amount of heat lost by the system is the amount of heat gained by the water, then we would be able to calculate an amount of enthalpy change for whatever is happening there. Okay, so there's a couple of different types of enthalpy changes that could be happening to a system that's inside of a calorimeter. All right, so one type of thing that could be happening would be a change of temperature at a constant state. All right, so an example of that would be, let's pretend that we put a hot block of metal inside that calorimeter. All right, well, in the beginning, you've got cool liquid water that's going to become warmer liquid water. All right, but with your system, you're going to have a hot block of solid metal becoming a cooler block of solid metal. So the state of matter doesn't change. All right, the thing that changes about the metal would be its temperature. All right, so we could calculate its delta H by using mCp delta T. All right, this would be the mass of that block. This would be the specific heat, and this would be the change in temperature. All right, another type of enthalpy change would be a changing state at a constant temperature. All right, let's pretend that this is a 0 degree piece of ice. All right, and if you just like ice water. All right, so let's pretend that this right here is room temperature water. All right, if we put that 0 degree piece of ice in there, all right, what's going to happen is that 0 degree ice is going to eventually turn into 0 degree water. All right, and that's going to involve heat going from the water into the piece of ice. All right, so we could calculate the amount of enthalpy change that occurs there by anytime the state of matter changes. There's these two equations, MHF and MHV. This is mass times the heat of what's called the heat of fusion. This is mass times the heat of vaporization. Both of these are equations that you use, hopefully used in sophomore chemistry. But these are some types of things that could be done with the calorimetry equations. All right. So one thing that you're expected to understand in the IB class is this little bit of data manipulation that we have to do in order to deal with reality. All right. So let's pretend that we put a hot block of metal into this calorimeter right here. Well, in a perfect world, this would be absolutely perfect insulation right here. And so what would happen is that the block would lose its heat, and it would be giving its heat energy to the water. All right, and so the water would warm up. So over time, the water is warming up. Again, what you're measuring here is the temperature of where the thermometer is. That's the measurement of the water temperature. All right, so the temperature is going up, and eventually the temperature of the block would be the same as the temperature of the water, and the water temperature is going to stop going up. But if this were to be absolutely perfect insulation and all the heat stays inside of the calorimeter, what would theoretically happen is that temperature would just stay there at that temperature forever. All right. But we know that in reality there is no such thing as a perfect insulator, and so eventually some of that heat is going to eventually make its way out of the calorimeter, and the temperature of the water is going to start to eventually drop. All right. So in reality, you end up getting something like this. When you drop the hot metal down in there, you initially get an increase in the water temperature, but eventually this thing stops losing heat to the water, but the hot water starts losing heat. Actually, it's actually been losing heat to the outside. It's just that the heat that it's absorbing from the metal has outpaced the heat that's lost. So in the beginning, you get an increase in the temperature, but once the heat loss to the outside outpaces the heat gain from your hot object, that's when it levels off, and eventually the heat loss is going to be significantly larger than any heat given off by your material, and the temperature is going to start dropping. All right. Well, again, theoretically, what we would like to have happen is all the heat stays in there, and we can measure a change in temperature. All right. That would be the difference in temperature here versus the difference in temperature here. That would be our delta T, and that's what we could put into this equation right here. All right. So in order to compensate for reality, all right, if we know this rate at which this calorimeter tends to lose heat to its surroundings, then we could take this slope right here and we could extrapolate that way up here. All right. And essentially that would give us our delta T, our change in temperature from here to the starting temperature. And what that would be, what the delta T would be in a perfect situation where, number one, this thing gave all of its heat to the water instantaneously. All right, and number two, all of the heat stayed within the calorimeter. All right, and we know that both of those are unrealistic, but by extrapolating this line right here, it allows us to calculate what that value would be. All right. Okay, so I can't say for certain whether you'll see a problem like this, but based on what I've seen, I would think that there is a decent likelihood that they would expect you to understand this little concept of extrapolating this line to compensate for the experimental reality of losing heat from your calorimeter.